Hello again, calculus students. As I mentioned in the last video, we were picking up on page 67. We just briefly talked about the properties of limits as x approaches positive and negative infinity, and these should look very familiar. They are, I believe, the exact same rules when we just talked about the limits as x approaches a particular number. So these shouldn't be terribly new, shouldn't be terribly interesting. Let's see how we're going to use these, though. On page 67, it starts by saying, let me get this set so we have a full screen to write on. That's a little big. All right. Anyways, so starting with example 3, it says we want to find the limit as x approaches infinity of 5x plus the sine of x all over x. Let me tidy this up just a shade. Okay, and I do apologize. I think I was talking a little bit quietly in the last video, so I'll try and speak up with this one, try and speak a little bit louder so you can hear this a little bit better. Now, they do say, notice for this solution, we're going to do a little bit of side work with this function here, 5x plus the sine of x all over x. They do a little bit of side work here saying, well, let's break this big fraction into two separate fractions, such as 5x over x plus sine of x over x. That is a legal move. These have the same denominator, so we're allowed to do that. Now, 5x over x, well, the x's are going to cancel out, just leaving us with 5. Now, the thing that's really nice about this is we may not know any of the information about this and how these limits work, but we do know how the limit of sine of x over x works. We just did that in one of our previous examples. So we're going to rewrite this as we're taking the limit as x approaches infinity of 5 plus sine of x over x. Oops, and I just rewrote the exact same thing. I lied. 5 plus the sine of x, and just the sine of x is over the x. Okay. So using our these properties, we can rewrite this as we're taking the limit as x approaches infinity of 5 plus the limit as x approaches infinity of sine of x over x. Let's take the part that we know. We know the limit as x approaches infinity of sine of x over x. We looked at this very much in depth. We know that this is 0. What is the limit of 5 as x approaches infinity? Well, the thing is 5 will always be 5. 5 will always be the horizontal line. 1, 2, 3, 4, 5. Well, 5 will always be the horizontal line that looks like this. Always, always, always going to be 5. So nothing too special about it. So the limit as x approaches anything of this constant number 5 is going to be 5. Well, then what is 5 plus 0? Well, it's 5. So the big thing here is that we realize that by rearranging this a little bit using some algebra techniques that we should hopefully be familiar with, and then saying, well, specifically if you want to know the rules, we use the sum rule, which is rule number 1 in theorem 5. We said, well, this is the same as taking the limit of just 5 and the limit of the sine of x plus x. And we found both of those limits and we added them together. So that should finish us up on page 67. Next part we're going to talk about is infinite limits as x approaches some a being some number. So let's, I'm going to flip to the next page here. And as you can see here, we have, I have a couple graphs of the tangent function. Now, on my calculator, what it is I went into the mode option. Let me show you exactly what I did. Here's my calculator. I'm going to turn it on, and I graphed the function, the tangent of x. Nothing special about that. Most of you have seen this before. If not, that's fine. Just for now, take it as it is. And I'm going to do a special zoom for this. If you hit the zoom button, you'll see these 7, 8 different options. Well, if we go to 7, this is a window specifically set for trigonometric functions. So it's called z-trig. So using that option, we take a look here and we see this funky thing where we have kind of this wavy thing and then a line and a wavy thing and a line. It's exactly what I have here. Right now my calculator is in what's called connected mode. If we go to the mode button and we go down a couple of spaces, you'll see that we have it in connected mode, which is good. Basically what it does is, well, let me talk about dot mode. Let's move it over to dot mode. We look at the graph. Graph, no. There we go. Notice how we just have dots. What the function has done is it has found some specific x values and then plotted the y values against it. It's just made the dots. In connected mode, it connects the dots for you. But the, I don't know, good or bad thing, depending on what you're looking for, is you get these lines. It connects these lines. Now, these lines are not actually on the graph. Some of you may know these. These are what we call vertical asymptotes. Go and pull out my line tool, and I will make them, I don't know, red's a good color, but we'll use this tealy blue color now. So what I mean by this is I can draw a line straight up from here. Oops. Let's see if it'll fix it. No, I lost the whole thing. Okay. We can draw a line straight up from here, and maybe I'll just adjust this afterward. That this function is not going to touch at all. And we have those asymptotes, is what these are called, asymptotes. They show up repeatedly in the trig function. Let's just do cloning this. Come on now. You see all these blue lines that I'm putting here, these are asymptotes for this graph. There are infinitely many asymptotes for the tangent graph, actually, and they all show up here. Now, in connected mode, the cool thing is that those asymptotes actually do show up because they connect this point up here that is infinitely high and this point way down here that's infinitely low, and it connects them. So those are vertical asymptotes. Just trying to see exactly what. And you'll actually find vertical asymptotes if you're looking in your textbook on page 68. You'll also find vertical asymptotes in the graph of some other functions we've looked at already. We go to y equals 1 over x. Remember, my calculator is still in dot mode. So if I were to graph this, notice how we have all the dots. There's actually a vertical asymptote shown here. Now it's hard to see, and if you're in connected mode, it'll actually just lie over the y-axis. But we do have a vertical asymptote, right? Well, can't do it on this calculator because I don't have ink for it. But yeah, right up here, right up and down there. So that is a vertical asymptote. Sorry, let me just see exactly what I want to say about this. And basically, how this is found, this is actually defined on page 68. It's whenever you have, if you're approaching a certain value from the left or from the right. So, for example, if we were approaching, we'll call it, this part right here would actually be specifically pi over 2. So let's just go ahead and jot this down here. Let's get one of these and make it green. Those of you familiar with trig, you'll know that this is pi over 2 right here. As our function gets closer and closer and closer to pi over 2, we get this, it goes up to infinity, we get this vertical asymptote. Or similarly, as we get closer, or from the left-hand side, as we get closer and closer to pi over 2, this goes to negative infinity, we get this vertical asymptote. So, and that's the formal definition. As you approach some sort of a real number, it goes to infinity or positive infinity. We get that vertical asymptote. We just did example 5, actually looking at the tangent function. So, the next and last thing I want to talk about in the remaining 5 minutes I have in this recording, roughly 5. Is end behavior. If you take a look at example 6, it lists a function f of x equals 3 x to the fourth minus 2x to the third plus 3x squared minus 5x plus 6. A very complicated function, lots of parts and pieces to it. And then they also want to look at graph g of x, 3x to the fourth. Well, the idea behind this is as these numbers get really, 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 really big, so f of x, I shouldn't say numbers, I should say these functions. As these functions get really, really big, so 3x to the fourth minus 2x cubed plus 3x squared minus 5x plus 6. Well, if we compare this to just the function of 3x to the fourth, early on these graphs are going to look way different. And by early on, I mean if you try 0, 1, 2, 3, so on and so forth. But as these numbers get infinitely big, as are diagrammed in your textbook, if you look at to the left, there's a graph of those functions with a very, very, very large y values. As these get bigger and bigger and bigger, they get to look more and more alike. And the reason for that being, if we take f of x divided by g of x, so this is going to be 3x to the fourth minus 2x to the third plus 3x squared plus 5x plus 6 all over 3x to the fourth. I do apologize for how messy this is. This is going to be equal to, if you were to do the reducing, 3x to the fourth over 3x to the fourth is 1 minus 2 over 3x plus 1 over x squared minus 5 over x to the third plus 2 x to the fourth. If you don't know how I got that, take a look in your textbook. Hopefully it'll explain. If not, we can ask about it in class. So what happens as our numbers get really, really big? Well, the 1 is going to stay as a 1. This, well, as the numbers get really, really big, the denominator is going to get super big, making this closer to 0. The denominator is going to get really, really big here, making this closer to 0, and this closer to 0, and this closer to 0. So as the numbers get really, really big, this gets close. This becomes 1. This is really the definition of end behavior. These two graphs have the same end behavior as we get bigger and bigger. If you take a look at the bottom of 69, that is the exact definition. That as the I should use this do this a little more formally. As the limit as x approaches infinity of one function f over g, if that is equal to 1, then you can say that that will represent G is a right end behavior model, and then if you go to negative infinity, it would be a left end behavior model. So I know that's a little bit complicated. I'm just trying to see here. There are a couple of examples going on. There's example 7 and example 8. I think I want to do example 8 real quick. Yeah, 8A I think is in particular is the one that I want to look at. Give me just a moment here. I apologize. Maybe I'm not going to do it because I do see I have only a couple minutes left. I don't want to go much past 15 minutes or I won't be able to upload the video. But we can take a look at these in class. To be perfectly honest with you, I didn't focus on these too much last year. But what I want you to do is I want you to look at examples 7, 8, 9, and 10, especially using substitution. I'll probably actually talk about example 10 in class. But take a look at these, and you should be prepared to do your assignment. If you have any questions, you can either post them as, I believe, comments to this video, or you can post them on the actual assignment homework. So any questions, let me know. And if I need to throw up another supplemental video, I will be glad to do so. Best of luck as you are working on your calculus assignments. We'll see you on Tuesday.